Picture this. In a fraction of a second, a single cosmic explosion unleashes more energy than our Sun will produce in its entire 10 billion year lifetime. This isn't science fiction, it's a gamma-ray burst, one of the most powerful and mysterious events in the universe. And it's just the beginning. From hypernovas that outshine entire galaxies to neutron star collisions that forge gold in the depths of space, the universe is a stage for some of the most mind-blowing spectacles imaginable. But what causes these colossal events? Why do they happen? And what can they teach us about the cosmos? In this video, we're diving into 25 jaw-dropping facts about the universe's most energetic events, phenomena so extreme they defy imagination. So buckle up, because we're about to explore the wildest, most explosive corners of space, where the rules of physics are pushed to their limits and the universe reveals its most dazzling secrets. Ready to have your mind blown? Let's go. Now, let's zoom in on the first of these cosmic powerhouses, gamma-ray bursts. These are not just any explosions, they are the most powerful blasts the universe has to offer. Imagine for a moment a single burst releasing more energy in a few seconds than our Sun will emit over its entire 10 billion year lifespan. That's the sheer scale we're talking about. But what exactly are gamma-ray bursts? They are intense flashes of gamma rays, the most energetic form of light, originating from distant galaxies. These bursts are so bright, they can outshine entire galaxies for a brief moment, even from billions of light years away. So how do we detect them? Satellites like NASA, Swift and Fermi are constantly scanning the skies for these fleeting events. When a gamma-ray burst occurs, these instruments pick up the initial flash of gamma rays, followed by an afterglow that can be observed in X-rays, visible light, and even radio waves. This afterglow helps scientists pinpoint the burst's location and study its properties in detail. But here's the kicker: despite decades of research, the origins of gamma-ray bursts remain shrouded in mystery. We know they come in two main types: long and short bursts. Long bursts, lasting more than 2 seconds, are thought to result from the collapse of massive stars into black holes. Short bursts, lasting less than 2 seconds, are likely caused by the collision of neutron stars. Yet, the exact mechanisms behind these cataclysmic events are still being unraveled. What makes gamma-ray bursts truly mind-bending is their energy output. In just a few seconds, they can release as much energy as a supernova, but in a much shorter time frame. To put it in perspective, if a gamma-ray burst occurred within a few thousand light-years of Earth, it could strip away our ozone layer with devastating consequences for life on our planet. Thankfully, such events are incredibly rare. So, why are gamma-ray bursts so important? They're not just cosmic fireworks, they're windows into the most extreme environments in the universe. By studying them, we can learn about the birth of black holes, the behavior of matter under extreme conditions, and even the expansion of the universe itself. And as we continue to unravel their secrets, one thing is clear: gamma-ray bursts are a testament to the raw, unfathomable power of the cosmos. Next up, we'll dive into how these bursts are linked to the birth of black holes, a process as fascinating as it is destructive. Stay tuned. Now, let's take a closer look at one of the most dramatic events tied to gamma-ray bursts, the birth of a black hole. Picture this: a massive star, many times heavier than our Sun, reaching the end of its life. After burning through its nuclear fuel, the star's core can no longer support its own weight. What happens next is nothing short of cosmic chaos. The star's core collapses under its own gravity, triggering a cataclysmic explosion known as a supernova. But in some cases, the collapse doesn't stop there. If the core is massive enough, it continues to implode, crushing itself into an infinitely dense point called a singularity. This is the moment a black hole is born. As the black hole forms, it unleashes an incredible amount of energy. Some of this energy is channeled into powerful jets of particles and radiation, shooting out at nearly the speed of light. These jets are what we observe as gamma-ray bursts. In fact, long gamma-ray bursts, which last more than 2 seconds, are often linked to this process known as a hypernova. The sheer power of this event is staggering. In just a few moments, the collapsing star releases more energy than our Sun will emit over its entire lifetime. And while the black hole itself remains hidden, its birth is marked by one of the most energetic phenomena in the universe. But how do we know all this? Thanks to advanced simulations and animations, scientists can recreate these events in stunning detail. These visuals show the star's core collapsing, the formation of the black hole, and the jets of energy bursting forth. They help us understand not just the mechanics of black hole formation, but also the role these events play in shaping the cosmos. So, the next time you hear about a gamma-ray burst, remember, it might just be the birth cry of a black hole, a cosmic event so powerful it reshapes our understanding of the universe. Up next, we'll explore how these bursts are connected to another extreme phenomenon, hypernova. Stay tuned. Now, let's dive into something even more explosive than a supernova hypernova. Think of these as supernovas on steroids, packing an unimaginable punch. While a regular supernova is already one of the most energetic events in the universe, a hypernova takes that energy and cranks it up to an entirely new level. Hypernova occur when a star is so massive, often dozens of times heavier than our Sun, that its collapse doesn't just create a supernova. Instead, the star's core collapses directly into a black hole, releasing an extraordinary amount of energy in the process. This energy isn't just a flash in the pan, it's channeled into incredibly powerful jets of particles and radiation, which we observe as gamma-ray bursts. What sets hypernova apart from regular supernovas is not just their energy output but also their aftermath. While a typical supernova leaves behind a neutron star or a black hole, a hypernova's explosion is so violent that it can completely obliterate the star, leaving nothing but a black hole and a massive shockwave that ripples through space. These events are also key players in the universe's chemical evolution. The sheer force of a hypernova can forge heavy elements like gold and platinum, scattering them across the cosmos. This means that the bling you're wearing might owe its existence to one of these cosmic explosions billions of years ago. But here's the kicker: hypernova are rare. They require stars so massive that they're on the extreme end of the cosmic scale. Yet, when they do occur, they leave an indelible mark on the universe, shaping galaxies and seeding the cosmos with the building blocks of life. So, while supernovas are awe-inspiring, hypernova remind us that the universe always has a way of upping the ante. Next, we'll explore what happens after the initial burst, the afterglow of gamma-ray bursts, and why it's so crucial for scientists to study. Stay tuned. Now, let's shift our focus to what happens after the initial explosion, the afterglow of gamma-ray bursts. While the burst itself lasts only seconds or minutes, the afterglow can linger for days, weeks, or even months, offering scientists a treasure trove of information. This afterglow is essentially the fading echo of the explosion, visible across a wide range of wavelengths, from X-rays to visible light and even radio waves. When a gamma-ray burst occurs, the initial flash is so intense that it can outshine entire galaxies. But as the energy dissipates, it interacts with the surrounding gas and dust, creating a glowing aftermath. This afterglow is like a cosmic fingerprint, revealing details about the burst's environment, the material it passed through, and even the nature of the explosion itself. Observing the afterglow across different wavelengths is key to piecing together the full story. X-rays, for example, help scientists track the high-energy processes at play, while visible light provides clues about the chemical composition of the surrounding material. Radio waves, on the other hand, can reveal how the shock waves from the burst propagate through space. Studying the afterglow isn't just about understanding the burst itself, it's also a window into the broader universe. By analyzing how the light from the afterglow changes over time, researchers can measure distances across the cosmos, probe the structure of galaxies, and even test theories about the expansion of the universe. But here's the catch: capturing the afterglow requires quick action. Satellites like NASA's Swift telescope are designed to detect gamma-ray bursts almost instantly and alert ground-based observatories to point their instruments at the right patch of sky. This rapid response is crucial because the afterglow fades quickly, and every second counts in gathering data. So, while the gamma-ray burst itself is a fleeting moment of cosmic violence, its afterglow tells a much longer story, one that helps us unravel the mysteries of the universe's most energetic events. Next, we'll explore the role of magnetars, those highly magnetized neutron stars, and how they might be connected to these explosive phenomena. Stay with us. Now, let's turn our attention to one of the most fascinating players in the cosmic drama of gamma-ray bursts, magnetars. These highly magnetized neutron stars are like the universe's ultimate powerhouses, packing an unimaginable amount of energy into a relatively small package. But what exactly makes them so special, and how do they connect to the explosive events we've been discussing? Magnetars are born from the remnants of massive stars that have gone supernova. When these stars collapse, they leave behind a dense core, a neutron star. But in the case of magnetars, this core is no ordinary neutron star. It's equipped with a magnetic field so intense that it defies comprehension. To put it in perspective, a magnetar's magnetic field can be a quadrillion times stronger than Earth's. That's a 1 followed by 15 zeros. This incredible magnetic power doesn't just sit idle. It can trigger some of the most energetic events in the universe, including gamma-ray bursts. When a magnetar's magnetic field becomes unstable, often due to starquakes or sudden shifts in its crust, it can release a colossal amount of energy in the form of gamma rays. These bursts are so powerful that they can outshine entire galaxies, even if only for a brief moment. But here's where it gets even more intriguing. Some scientists believe that magnetars might be responsible for a specific type of gamma-ray burst known as a short burst. These bursts last only a few seconds, but they pack a punch that rivals their longer counterparts. The theory is that when two neutron stars collide or a magnetar undergoes a catastrophic event, the resulting explosion could produce one of these short, intense bursts. What makes magnetars truly unique is their ability to channel energy in such a focused and explosive way. Their magnetic fields act like cosmic accelerators, driving particles to near light speeds and generating the intense radiation we observe as gamma-ray bursts. This process not only highlights the incredible forces at play in the universe, but also gives us a glimpse into the extreme conditions that exist around these exotic objects. So, while magnetars might be small in size, their impact on the cosmos is anything but. They remind us that even the tiniest objects in the universe can unleash unimaginable power, shaping the very fabric of space and time. Next, we'll dive into the physics behind relativistic jets and how they play a key role in the energy output of gamma-ray bursts. Stay tuned. Now, let's shift gears and explore one of the most mind-bending aspects of gamma-ray bursts, relativistic jets. These jets are like cosmic particle accelerators, shooting out matter at speeds so close to the speed of light that they challenge our understanding of physics itself. But what exactly are these jets, and how do they contribute to the incredible energy we observe in gamma-ray bursts? Relativistic jets are narrow beams of ionized matter. Think of them as supercharged streams of particles that are ejected from the poles of a collapsing star or emerging neutron star. What makes them truly extraordinary is their speed. These jets travel at velocities approaching the speed of light, which is about 299,792,458 meters per second. To put it simply, they're moving so fast that time and space behave differently for them compared to us. This is where Einstein's theory of relativity comes into play, giving these jets their name. But how do these jets form? It all starts with the intense gravitational and magnetic forces at work during a gamma-ray burst. When a massive star collapses or two neutron stars collide, the resulting explosion creates a swirling disk of superheated material around the newly formed black hole or neutron star. This disk acts like a cosmic engine, funneling energy and matter into two narrow beams that shoot out from the poles. The magnetic fields around the object twist and channel this material, accelerating it to nearly the speed of light. The energy released in these jets is staggering. As the particles in the jet collide with surrounding gas and dust, they produce shock waves that generate gamma rays, X-rays, and other forms of high-energy radiation. This is what we detect as a gamma-ray burst. The jets are so focused and energetic that even from billions of light years away, they can outshine entire galaxies for a brief moment. What's even more fascinating is that these jets aren't just random bursts of energy, they're highly structured. Scientists believe that the magnetic fields within the jets play a crucial role in keeping them tightly collimated or focused over vast distances. Without this magnetic guidance, the jets would spread out and lose their incredible intensity long before reaching us. Relativistic jets are a testament to the extreme conditions that exist in the universe. They show us how matter and energy can be harnessed and accelerated to unimaginable speeds, creating some of the most powerful explosions we've ever observed. And while we've made great strides in understanding these jets, they still hold many mysteries. For instance, why do some gamma-ray bursts produce jets while others don't? And what exactly determines the direction and intensity of these jets? As we continue to study these cosmic phenomena, one thing is clear. Relativistic jets are a key piece of the puzzle when it comes to understanding gamma-ray bursts and the universe's most energetic events. Next, we'll take a closer look at the mystery of short gamma-ray bursts and what sets them apart from their longer counterparts. Stay tuned. Now, let's dive into one of the most intriguing puzzles in the cosmos, short gamma-ray bursts. While we've been exploring the incredible power of long gamma-ray bursts, their shorter counterparts are equally fascinating and far more mysterious. Unlike long bursts, which can last from a few seconds to several minutes, short gamma-ray bursts are over in the blink of an eye, lasting less than 2 seconds. But don't let their brief duration fool you. These events pack a punch that rivals their longer siblings. So what makes short gamma-ray bursts so different? The key lies in their origins. While long bursts are typically linked to the collapse of massive stars, short bursts are thought to arise from the collision of two neutron stars. Imagine two ultra-dense stellar remnants, each about the size of a city but with the mass of our Sun, spiraling toward each other in a cosmic dance. When they finally collide, the resulting explosion releases an immense amount of energy in the form of a short gamma-ray burst. This merger also creates ripples in space-time known as gravitational waves, which scientists can detect here on Earth. But why are short gamma-ray bursts harder to study? For starters, their fleeting nature makes them incredibly challenging to catch. By the time telescopes can lock onto their location, the burst itself is often already over. This leaves scientists with only the afterglow, a faint echo of the explosion, to piece together what happened. Additionally, because these bursts are so brief, they produce less data for researchers to analyze compared to longer bursts. This lack of information makes it difficult to fully understand the mechanisms behind them. Another layer of mystery is the environment in which these bursts occur. Neutron star mergers are rare events, and they often happen in distant galaxies, making them harder to observe. Even when we do detect a short gamma-ray burst, pinpointing its exact location requires a coordinated effort from multiple observatories around the world. This teamwork is crucial as it allows scientists to study the burst across different wavelengths of light, from gamma rays to radio waves, to get a more complete picture. Despite these challenges, short gamma-ray bursts have given us some groundbreaking insights. For example, the detection of gravitational waves from a neutron star merger in 2017 marked a turning point in astrophysics. This event, known as GW170817, not only confirmed the connection between neutron star collisions and short gamma-ray bursts, but also provided evidence for the creation of heavy elements like gold and platinum in these cosmic explosions. The mystery of short gamma-ray bursts continues to captivate scientists, offering a glimpse into some of the most extreme environments in the universe. As we refine our detection methods and build more advanced instruments, we're inching closer to unraveling their secrets. Next, we'll explore another fascinating outcome of neutron star collisions, the Kilonova explosion. Stay tuned. Now, let's take a closer look at the spectacular phenomenon of neutron star collisions. These cosmic encounters are not just the source of short gamma-ray bursts, they're also one of the most extreme events in the universe. When two neutron stars, each with a mass greater than our Sun but compressed into a sphere no larger than a city, collide, the result is nothing short of explosive. The sheer force of their merger releases an incredible amount of energy, not only in the form of gamma rays but also as gravitational waves, ripples in the fabric of spacetime itself. The detection of gravitational waves from neutron star collisions has revolutionized our understanding of the universe. In 2017, the historic event known as GW170817 marked the first time scientists observed both gravitational waves and light from the same cosmic event. This groundbreaking discovery confirmed that neutron star mergers are indeed the source of short gamma-ray bursts, solving a long-standing mystery in astrophysics. But it also did something even more profound. It opened a new window into the universe, allowing us to study these events in ways we never could before. Gravitational waves provide a unique perspective on neutron star collisions. Unlike light, which can be absorbed or scattered by cosmic dust, gravitational waves travel unimpeded through the universe. This means they carry information about the collision that light alone cannot reveal. By analyzing these waves, scientists can determine the masses of the neutron stars, the distance to the collision, and even the properties of the material ejected during the explosion. This data is invaluable for understanding the physics of these extreme environments, but the significance of neutron star collisions goes beyond just gravitational waves. These events are also cosmic factories for some of the heaviest elements in the universe. When neutron stars collide, they spew out a dense cloud of neutron-rich material. In this chaotic environment, rapid nuclear reactions occur, creating elements like gold, platinum, and uranium. In fact, it's estimated that a single neutron star merger can produce enough gold to outweigh the entire Earth. This discovery has reshaped our understanding of where the elements in our universe come from, linking the origins of precious metals to the most violent events in space. Studying neutron star collisions is no easy task. These events are rare, occurring only a few times per million years in a galaxy like our own. Detecting them requires a global network of observatories, from gravitational wave detectors like LIGO and Virgo to telescopes that observe across the electromagnetic spectrum. Each detection provides a new piece of the puzzle, helping us build a more complete picture of these extraordinary events. As we continue to explore the universe, neutron star collisions remain a key area of research. They not only shed light on the origins of gamma-ray bursts and heavy elements, but also offer insights into the fundamental laws of physics. From the behavior of matter under extreme conditions to the nature of spacetime itself, these collisions are a treasure trove of scientific discovery. Next, we'll delve into the aftermath of these cosmic explosions, the dazzling Kilonova. Stay with us as we uncover more about this spectacular phenomenon. Now, let's turn our attention to the dazzling aftermath of neutron star collisions, the Kilonova explosion. When two neutron stars merge, the resulting explosion is so powerful that it outshines entire galaxies for a brief moment. This spectacular event, known as a kilonova, is not just a visual marvel, it's also a cosmic factory for some of the heaviest elements in the universe. During a kilonova, the collision ejects a massive amount of neutron-rich material into space. In this chaotic environment, rapid nuclear reactions take place, transforming the ejected material into heavy elements like gold, platinum, and uranium. These elements, which are rare and precious on Earth, are forged in the heart of these explosive events. In fact, scientists estimate that a single kilonova can produce enough gold to outweigh the entire Earth. This discovery has fundamentally changed our understanding of where heavy elements come from, linking their origins to the most violent and energetic events in the cosmos. Kilonovas are not just important for creating heavy elements, they also provide a unique opportunity to study the behavior of matter under extreme conditions. The intense heat and pressure generated during the explosion allow scientists to observe processes that cannot be replicated in any laboratory on Earth. By analyzing the light emitted by kilonovas, researchers can learn about the properties of the ejected material, the speed at which it was expelled, and even the conditions inside neutron stars themselves. One of the most fascinating aspects of kilonovas is their role in shaping the chemical composition of the universe. Before the discovery of kilonovas, scientists believed that most heavy elements were produced in supernovas. However, kilonovas have proven to be equally, if not more, important in creating these elements. This means that the gold in your jewelry or the platinum in your car's catalytic converter likely originated from a neutron star collision billions of years ago. Studying kilonovas is a challenging but rewarding endeavor. These events are rare, occurring only a few times per million years in a galaxy like our own. Detecting them requires a coordinated effort from observatories around the world, using both gravitational wave detectors and telescopes that observe across the electromagnetic spectrum. Each kilonova detection provides new insights into the processes that shape our universe, from the creation of heavy elements to the behavior of matter under extreme conditions. As we continue to explore the cosmos, kilonovas remain a key area of research. They not only help us understand the origins of the elements that make up our world, but also offer a glimpse into the most extreme environments in the universe. Next, we'll explore the incredible energy output of gamma-ray bursts and how they compare to other cosmic events. Stay tuned as we uncover more about these awe-inspiring phenomena. Now, let's shift our focus to the staggering energy unleashed by gamma-ray bursts. These cosmic explosions are so powerful that they dwarf even the most energetic events we've discussed so far. To put it into perspective, a single gamma-ray burst can release more energy in just a few seconds than the Sun will emit over its entire 10 billion-year lifetime. That's right, in the blink of an eye, a gamma-ray burst outshines the cumulative energy output of our nearest star. But how does this compare to other cosmic phenomena? Let's take supernovas, for example. While a supernova is one of the most violent events in the universe, releasing energy equivalent to about 10 octillion nuclear bombs, a gamma-ray burst can be up to 100 times more energetic. Even solar flares, which are massive eruptions on the Sun's surface, pale in comparison. A typical solar flare releases energy equivalent to millions of hydrogen bombs, but that's still only a tiny fraction of what a gamma-ray burst can produce. To make this even more relatable, imagine the Sun's energy output over its entire lifespan compressed into just a few seconds. That's the kind of power we're talking about with gamma-ray bursts. It's like comparing a campfire to a volcanic eruption. Both are impressive, but the scale is entirely different. This immense energy is what makes gamma-ray bursts some of the most extreme events in the universe, capable of lighting up the cosmos from billions of light-years away. What's truly mind-blowing is that this energy is concentrated into narrow beams known as relativistic jets, which travel at nearly the speed of light. These jets are so focused that if one were pointed directly at Earth, we'd detect its effects even from the farthest reaches of the observable universe. Fortunately, such events are rare, but they serve as a reminder of just how dynamic and energetic the cosmos can be. As we continue to explore these incredible phenomena, the sheer scale of their energy output challenges our understanding of physics and the limits of what's possible in the universe. Next, we'll dive into the vast distances these bursts travel and how we detect them from the edge of the observable universe. Stay with us as we uncover more about these cosmic powerhouses. Now, let's journey into the vastness of space to explore just how far gamma-ray bursts can travel. These incredible events are not only powerful but also incredibly distant, often detected from billions of light-years away. To put that into perspective, when we observe a gamma-ray burst, we're essentially looking back in time, witnessing an event that occurred when the universe was much younger. This makes gamma-ray bursts some of the most distant and ancient phenomena we can detect. The sheer distance of these bursts presents unique challenges for scientists. For one, the farther away an event is, the fainter it appears to us here on Earth. Even though gamma-ray bursts are incredibly energetic, their light has to travel across unimaginable distances, losing intensity along the way. This means that by the time the light reaches us, it's often extremely faint, requiring highly sensitive instruments to detect it. Satellites like NASA, Swift, and Fermi are specifically designed to pick up these faint signals, but even with advanced technology, studying such distant events is no easy task. Another challenge is the time delay caused by the vast distances. Since light takes time to travel, what we're seeing now actually happened billions of years ago. This means we're observing gamma-ray bursts from a time when the universe was very different, younger, hotter, and filled with fewer galaxies. Understanding these bursts requires us to piece together the conditions of the early universe, adding another layer of complexity to their study. Despite these challenges, detecting gamma-ray bursts from such immense distances has its advantages. Because they are so far away, they act as cosmic beacons, helping us map the structure of the universe and understand how it has evolved over time. They also provide clues about the formation of early stars and galaxies, offering a glimpse into the universe's infancy. As we continue to push the boundaries of our observational capabilities, gamma-ray bursts remain one of the most fascinating tools for exploring the cosmos. Next, we'll take a closer look at the role of satellites in detecting these bursts and how they've revolutionized our understanding of these distant, energetic events. Stay tuned as we uncover more about the technology that brings the universe's most powerful explosions into focus. Now, let's turn our attention to the incredible technology that makes it possible to detect and study gamma-ray bursts, satellites. Without these advanced instruments, we'd be completely in the dark about these distant cosmic explosions. Satellites like NASA, Swift, and Fermi are at the forefront of this mission, acting as our eyes in the sky, capturing the faint signals of gamma-ray bursts from billions of light-years away. The Swift satellite, launched in 2004, is specifically designed to detect gamma-ray bursts and quickly pinpoint their location in the sky. Here's how it works. When Swift detects a burst, it immediately swings into action, rotating its telescopes to observe the event in multiple wavelengths, from gamma rays to visible light. This rapid response is crucial because gamma-ray bursts are fleeting, often lasting only a few seconds. By capturing the afterglow in different wavelengths, Swift provides scientists with a wealth of data about the burst's origin, energy, and environment. Fermi, on the other hand, takes a broader approach. Launched in 2008, the Fermi Gamma Ray Space Telescope is equipped with instruments that can detect gamma rays across a wide range of energies. This allows Fermi to observe not only gamma-ray bursts but also other high-energy phenomena like pulsars and black holes. One of Fermi's key contributions is its ability to measure the energy spectrum of gamma-ray bursts, helping scientists understand the physics behind these explosive events. Together, Swift and Fermi have revolutionized our understanding of gamma-ray bursts. They've provided critical insights into how these bursts are produced, what causes them, and what they can tell us about the universe. For example, data from these satellites have confirmed that gamma-ray bursts are linked to the collapse of massive stars and the mergers of neutron stars, two of the most energetic processes in the cosmos. But it's not just about the science. These satellites have also made gamma-ray bursts more accessible to the public. Thanks to their real-time data sharing, amateur astronomers and space enthusiasts can follow along as new bursts are detected, making these cosmic events a shared experience for people around the world. As we continue to rely on satellites like Swift and Fermi, our ability to study gamma-ray bursts will only improve. These instruments are not just tools for scientists, they're gateways to understanding the universe's most powerful explosions. Next, we'll explore what would happen if a gamma-ray burst occurred closer to home and the potential dangers it could pose to life on Earth. Stay tuned as we dive into the risks and realities of these cosmic powerhouses. Now, let's shift our focus to a chilling possibility. What if a gamma-ray burst happened close to Earth? While these events are incredibly rare, the consequences would be nothing short of catastrophic. Imagine a burst of energy so powerful that it could outshine an entire galaxy, unleashed just a few thousand light years away from our planet. The effects would be immediate and devastating. First, the intense radiation from the burst would strip away Earth's ozone layer, leaving the surface exposed to harmful ultraviolet rays from the sun. This would disrupt ecosystems, damage crops, and increase the risk of skin cancer for all living organisms. But that's just the beginning. The burst would also produce a massive influx of high-energy particles, creating a cascade of secondary radiation that could further harm life on Earth. The atmosphere itself would undergo dramatic changes. The gamma rays would ionize the air, potentially triggering chemical reactions that produce nitrogen oxides. These compounds could deplete the ozone layer even further, compounding the damage. Over time, the loss of the ozone layer would lead to a significant drop in global temperatures, disrupting weather patterns and causing widespread environmental stress. But why should we be concerned if gamma-ray bursts are so rare? The truth is, while the likelihood of such an event happening in our cosmic neighborhood is extremely low, the sheer scale of the destruction makes it a terrifying prospect. Scientists estimate that a gamma-ray burst within 6,000 light-years of Earth could cause a mass extinction event. The good news, the closest known gamma-ray bursts are billions of light-years away, far enough to pose no immediate threat. Still, the possibility serves as a reminder of how fragile life on Earth can be in the face of the universe's most energetic events. It also highlights the importance of studying these phenomena, not just to satisfy our curiosity, but to better understand the risks they might pose in the distant future. Next, we'll explore how gamma-ray bursts are connected to the birth of stars and the evolution of galaxies, revealing yet another layer of their cosmic significance. Stay with us as we uncover more about these extraordinary events. Now, let's turn our attention to the fascinating connection between gamma-ray bursts and the birth of stars. These explosive events aren't just random cosmic fireworks, they're deeply tied to the life cycles of the most massive stars in the universe. In fact, gamma-ray bursts often occur in regions where stars are being born at an incredible rate, known as star-forming regions. These areas are like cosmic nurseries, filled with gas, dust, and young, massive stars that burn bright and fast. Massive stars, those that are many times heavier than our Sun, play a crucial role in producing gamma-ray bursts. These stars live fast and die young, ending their lives in spectacular explosions. When a massive star exhausts its fuel, it collapses under its own gravity, triggering a supernova or even a hypernova. In some cases, this collapse leads to the formation of a black hole, and the energy released during this process can produce a gamma-ray burst. Essentially, gamma-ray bursts are the final, dramatic cries of these colossal stars as they meet their end. But why do these bursts tend to happen in star-forming regions? It's because these areas are rich in the raw materials needed to create massive stars. The dense clouds of gas and dust provide the perfect environment for stars to form, and the most massive ones are the ones most likely to produce gamma-ray bursts when they die. This means that gamma-ray bursts can act as cosmic signposts, pointing us to regions where stars are being born and galaxies are evolving. The implications of this connection are profound. By studying gamma-ray bursts, scientists can learn more about how stars form and how galaxies grow over time. These bursts give us a glimpse into the early universe when star formation was at its peak and help us understand the processes that shape galaxies today. They also remind us that the universe is a dynamic, ever-changing place where the birth and death of stars are intertwined in a cosmic dance of creation and destruction. As we continue to explore the mysteries of gamma-ray bursts, we'll see how they're not just isolated events but part of a larger story, one that connects the lives of stars to the evolution of galaxies. Next, we'll dive into the story of the first gamma-ray burst ever detected, a discovery that changed our understanding of the universe forever. Stay tuned as we uncover more about these extraordinary cosmic phenomena. Now, let's step back in time to a moment that changed our understanding of the cosmos forever, the first observed gamma-ray burst. It was the year 1967, and the Cold War was in full swing. The United States had launched a series of satellites called Vela, designed to monitor nuclear explosions in space as part of a treaty compliance effort. But what these satellites detected was something entirely unexpected. On July 2, 1967, the Vela satellites picked up a sudden, intense burst of gamma rays. At first, scientists were baffled. The signal didn't match anything they had seen before. It wasn't coming from Earth, and it didn't fit the profile of a nuclear explosion. For years, the data remained classified as researchers struggled to make sense of what they had found. Was it a secret weapon, a malfunction in the equipment, or something entirely new? It wasn't until the early 1970s that the truth began to emerge. Scientists realized that the burst wasn't man-made, it was cosmic. This marked the discovery of the first gamma-ray burst, a phenomenon that would revolutionize our understanding of the universe. The Vela satellites had accidentally stumbled upon one of the most energetic events in the cosmos, and it was coming from deep space. What made this discovery even more remarkable was the sheer mystery surrounding it. Gamma-ray bursts were unlike anything astronomers had ever observed. They were incredibly brief, lasting only seconds, but packed more energy than the sun would emit in its entire lifetime, and they seemed to come from random directions in the sky with no obvious source. For decades, the origin of these bursts remained one of the greatest puzzles in astrophysics. The realization that gamma-ray bursts were cosmic in origin opened up a whole new field of study. It showed us that the universe is far more dynamic and violent than we had imagined. These bursts weren't just rare anomalies, they were windows into some of the most extreme processes in the cosmos, from the collapse of massive stars to the mergers of neutron stars. The discovery of the first gamma-ray burst was a turning point in astronomy. It reminded us that sometimes the most groundbreaking discoveries come from the most unexpected places. And it set the stage for decades of research that would uncover the true nature of these extraordinary events. Next, we'll explore the most distant gamma-ray burst ever detected, a record-breaking event that pushed the limits of our observational capabilities. Stay with us as we journey to the edge of the observable universe. Now, let's take a leap into the farthest reaches of space and time, where we encounter the most distant gamma-ray burst ever detected. This record-breaking event, known as GRB 090429b, was observed in April 2009, and it came from a staggering distance of over 13 billion light-years away. To put that into perspective, this burst occurred when the universe was just a fraction of its current age, only about 600 million years old. It's like catching a glimpse of the universe in its infancy, a time when the first stars and galaxies were just beginning to form. What makes this gamma-ray burst so extraordinary is not just its distance, but what it tells us about the early universe. Detecting such an event from so far away is like finding a needle in a cosmic haystack. It required a combination of advanced technology and a bit of luck. Satellites like NASA, Swift, and Fermi were instrumental in capturing the initial burst, while ground-based telescopes followed up to measure its distance. The light from this burst had traveled for over 13 billion years before reaching us, making it one of the oldest and most distant objects ever observed. The significance of this discovery goes beyond just setting a record. Gamma-ray bursts like this one act as cosmic beacons, illuminating the conditions of the early universe. By studying the light from these bursts, scientists can learn about the composition of the universe at that time, including the presence of elements like hydrogen and helium. This particular burst provided crucial insights into the era of reionization, a period when the first stars and galaxies began to ionize the surrounding gas, fundamentally changing the structure of the universe. But detecting such distant events also pushes the limits of our observational capabilities. The farther we look into space, the fainter and more challenging these signals become to detect. This gamma-ray burst was so distant that its light was stretched or redshifted to an extreme degree, making it visible only in the infrared spectrum. It's a testament to the ingenuity of astronomers and the power of modern telescopes that we can even observe such events at all. The discovery of the most distant gamma-ray burst reminds us of the vastness of the universe and the incredible journey light takes to reach us. It also highlights the importance of pushing the boundaries of our technology to explore the cosmos. As we continue to search for these distant bursts, we're not just uncovering the history of the universe, we're also testing the limits of what we can see and understand. Next, we'll explore how gamma-ray bursts are helping us unravel one of the greatest mysteries of the cosmos, the nature of dark energy. Stay tuned as we dive deeper into the secrets of the universe. Now, shifting our focus to one of the most profound mysteries of the cosmos, let's explore how gamma-ray bursts are helping us understand dark energy. Dark energy, the mysterious force driving the accelerated expansion of the universe, has puzzled scientists for decades. But here's where gamma-ray bursts come into play. They serve as powerful tools to measure this expansion and shed light on the nature of dark energy. Gamma-ray bursts are incredibly bright and can be detected from vast distances, making them ideal cosmic yardsticks. By measuring the redshift of these bursts, how much their light has stretched as the universe expands, scientists can calculate how fast the universe was expanding at different points in time. This information is crucial because it helps us map the rate of cosmic expansion over billions of years, revealing how dark energy has influenced the universe's growth. Think of it like this: gamma-ray bursts act as mile markers on a cosmic highway. Each burst gives us a snapshot of the universe's expansion at a specific moment in its history. By comparing these snapshots, astronomers can piece together a timeline of how dark energy has shaped the cosmos. This method has already provided evidence that the universe's expansion is accelerating, a discovery that earned the Nobel Prize in Physics in 2011. But why are gamma-ray bursts so useful for this purpose? Unlike other cosmic markers such as supernovas, gamma-ray bursts are visible from much greater distances. This allows scientists to probe deeper into the universe's past, reaching back to a time when dark energy's influence was just beginning to take hold. Additionally, their intense brightness makes them easier to detect and study, even across billions of light years. The connection between gamma-ray bursts and dark energy is a perfect example of how studying the universe's most energetic events can unlock its deepest secrets. By using these bursts as cosmic probes, scientists are not only learning about the nature of dark energy, but also gaining insights into the ultimate fate of the universe. Will the expansion continue to accelerate indefinitely, or will dark energy's influence change over time? These are the questions gamma-ray bursts are helping us answer. As we continue to detect and analyze these bursts, we're not just exploring the universe's past, we're also charting its future. Next, we'll dive into the enigmatic world of ultra-long gamma-ray bursts, events that defy our current understanding and challenge us to rethink what we know about the cosmos. Stay tuned as we uncover more about these extraordinary phenomena. Now, let's turn our attention to a cosmic phenomenon that stretches the limits of what we thought we knew about gamma-ray bursts. Ultra-long gamma-ray bursts are a rare and mysterious class of these events, lasting not seconds or minutes but hours. That's right, hours of intense, high-energy radiation pouring out into the universe, defying our expectations and challenging our understanding of these explosive events. So, what could possibly cause such an extended burst of energy? One leading theory points to the collapse of supermassive stars, far larger than the ones responsible for regular gamma-ray bursts. Imagine a star so massive that its core collapses not into a neutron star or a black hole, but into something even more extreme. As the star's outer layers fall inward, they create a prolonged release of energy, resulting in an ultra-long gamma-ray burst. This process is thought to be linked to the death of stars with masses tens or even hundreds of times greater than our Sun. Another intriguing possibility is that these bursts could be the result of a different kind of cosmic event altogether. Some scientists speculate that they might be caused by the tidal disruption of a star by a supermassive black hole. In this scenario, a star gets too close to a black hole and is torn apart by its immense gravitational pull. The debris from the star spirals into the black hole, releasing a torrent of energy over an extended period. This could explain why ultra-long gamma-ray bursts are so rare. They require a very specific and extreme set of conditions to occur. What makes these bursts even more fascinating is their potential to reveal new insights into the life cycles of the most massive stars and the behavior of black holes. By studying ultra-long gamma-ray bursts, astronomers can test theories about how stars evolve, how black holes grow, and how energy is released in the most extreme environments in the universe. Each burst is like a cosmic laboratory, offering a glimpse into processes that are otherwise impossible to observe directly. As we continue to detect and analyze these extraordinary events, we're not just solving a mystery, we're expanding our understanding of the universe's most extreme phenomena. Next, we'll explore how gamma-ray bursts might have left their mark on Earth's history, and whether these cosmic explosions could have influenced life on our planet. Stay with us as we uncover more about the universe's most energetic events. Now, let's shift our focus to a fascinating question that ties the cosmos directly to our own planet. Could gamma-ray bursts have played a role in shaping Earth's history? It's a thought-provoking idea, and one that scientists have been exploring for decades. Imagine a gamma-ray burst occurring relatively close to Earth within a few thousand light-years. The sheer energy released in such an event could have profound effects on our planet, potentially even triggering mass extinctions. One of the most compelling theories suggests that a gamma-ray burst could strip away a significant portion of Earth's ozone layer. Without this protective shield, harmful ultraviolet radiation from the sun would reach the surface, damaging ecosystems and threatening life. Some researchers have proposed that such an event might explain certain mass extinctions in Earth's past, like the Ordovician extinction around 440 million years ago. During this period, a sudden and dramatic loss of marine life occurred, and while the exact cause remains debated, a gamma-ray burst is one of the possibilities on the table. But proving this connection is no easy task. The evidence is indirect, relying on geological records and computer simulations. For example, scientists look for traces of sudden changes in the fossil record or chemical signatures in ancient rocks that could hint at a catastrophic event. However, these clues are often open to interpretation, and other factors like volcanic activity or asteroid impacts could produce similar effects. This makes it incredibly challenging to pinpoint gamma-ray bursts as the definitive cause of any specific extinction event. Another layer of complexity comes from the rarity of such events. Gamma-ray bursts are incredibly powerful, but they're also extremely rare, especially at distances close enough to affect Earth. Statistically, the likelihood of a gamma-ray burst occurring near our planet is very low, but over the vast timescales of Earth's history, it's not impossible. This rarity makes it difficult to gather concrete evidence, but it also underscores just how extraordinary these cosmic events are. Despite the challenges, studying the potential impact of gamma-ray bursts on Earth's history is more than just an academic exercise. It helps us understand the broader relationship between cosmic events and life on our planet. It also reminds us that Earth is part of a dynamic and sometimes dangerous universe, where even the most distant events can have far-reaching consequences. As we continue to explore this connection, we're not just piecing together the past, we're also preparing for the future. Understanding how gamma-ray bursts could affect Earth helps us assess potential risks and develop strategies to protect our planet. Next, we'll look ahead to the future of gamma-ray burst research and the exciting discoveries that await us as we push the boundaries of our knowledge. Stay tuned. Now, let's turn our gaze to the horizon of discovery and explore what the future holds for gamma-ray burst research. As our technology advances, so does our ability to unravel the mysteries of these cosmic explosions. Upcoming missions and cutting-edge telescopes are set to revolutionize our understanding, offering unprecedented insights into the universe's most energetic events. One of the most exciting developments on the horizon is the launch of next-generation space telescopes, like the European Space Agency's Athena mission. Scheduled for the 2030s, Athena will be equipped with state-of-the-art X-ray detectors capable of observing gamma-ray bursts and their afterglows with incredible precision. This will allow scientists to study the physics of these events in greater detail, from the behavior of relativistic jets to the environments surrounding black holes and neutron stars. Another groundbreaking project is the James Webb Space Telescope's successor, the Nancy Grace Roman Space Telescope. While primarily designed to study dark energy and exoplanets, its wide-field imaging capabilities will also make it a powerful tool for detecting gamma-ray bursts and their afterglows across vast distances. By capturing these events in multiple wavelengths, researchers hope to piece together a more complete picture of their origins and effects. On the ground, observatories like the Cherenkov Telescope Array are pushing the boundaries of gamma-ray astronomy. This network of telescopes will detect very high-energy gamma rays, providing new insights into the extreme environments where gamma-ray bursts occur. Combined with data from space-based instruments, these observations will help us understand how these bursts accelerate particles to such incredible energies. But it's not just about new telescopes. Advances in data analysis and artificial intelligence are also transforming the field. Machine learning algorithms are being developed to sift through vast amounts of data, identifying gamma-ray bursts more quickly and accurately than ever before. This will enable faster follow-up observations, allowing scientists to study the early stages of these events in real time. The future of gamma-ray burst research is brimming with potential. From uncovering the secrets of neutron star mergers to probing the earliest moments of the universe, these missions and technologies promise to deepen our understanding of the cosmos. As we continue to push the boundaries of exploration, one thing is certain: the universe still has countless surprises in store for us. Next, we'll dive into the role of supermassive black holes and their connection to some of the most energetic phenomena in the cosmos. Stay tuned. Now, shifting our focus to the heart of galaxies, let's explore the role of supermassive black holes in creating some of the universe's most energetic events. These cosmic giants, often millions or even billions of times more massive than our Sun, are not just lurking in the shadows, they're powerhouses of activity. One of their most spectacular displays comes in the form of quasars, the brightest objects in the universe. Quasars occur when supermassive black holes devour enormous amounts of gas and dust, heating it to extreme temperatures and causing it to glow with incredible intensity. This process releases staggering amounts of energy, outshining entire galaxies. But quasars are just the beginning. Supermassive black holes are also at the center of active galactic nuclei, or AN, which are regions of intense radiation and particle jets. These jets, traveling at nearly the speed of light, can stretch across millions of light years, carving through space and interacting with surrounding matter. In some cases, these jets are so powerful that they can trigger gamma-ray bursts when they collide with gas clouds or other celestial objects. This connection highlights how supermassive black holes are not just isolated phenomena but key players in the universe's most energetic events. Interestingly, supermassive black holes also play a role in shaping their galaxies. The energy they release can heat up surrounding gas, preventing it from collapsing to form new stars. This process, known as feedback, helps regulate the growth of galaxies and influences their evolution over billions of years. Without supermassive black holes, the universe as we know it might look very different. As we continue to study these colossal objects, we're uncovering more about their role in the cosmos. From powering quasars to influencing galaxy formation, supermassive black holes are central to understanding the universe's most energetic phenomena. Next, we'll turn our attention to another mysterious high-energy event, fast radio bursts. What are they, and how do they compare to gamma-ray bursts? Stay tuned to find out. Now, let's dive into another cosmic mystery that has puzzled scientists for years: fast radio bursts. These fleeting bursts of radio waves last just milliseconds, but they pack an incredible amount of energy. Imagine the energy of hundreds of millions of suns being released in a fraction of a second. That's the power of a fast radio burst. First discovered in 2007, these bursts have since been detected from all corners of the universe, often originating billions of light years away. But what makes them so fascinating is how little we know about their origins. Fast radio bursts, or FRB, are often compared to gamma-ray bursts because both are incredibly energetic and occur in the blink of an eye. However, while gamma-ray bursts are typically linked to the collapse of massive stars or neutron star collisions, the source of FRBs remains a mystery. Some theories suggest they could come from highly magnetized neutron stars, known as magnetars, while others propose they might be the result of collisions between dense objects like black holes or neutron stars. There's even speculation that FRBs could be signals from advanced extraterrestrial civilizations, though this idea remains highly speculative. One of the biggest challenges in studying FRBs is their unpredictability. Unlike gamma-ray bursts, which often leave behind an afterglow that can be studied, FRBs vanish almost instantly, leaving little trace. This makes them incredibly difficult to detect and analyze. However, advancements in radio telescopes and detection technology have allowed scientists to catch more of these elusive events in recent years. Some FRBs even repeat, giving researchers a rare opportunity to study them in greater detail. The search for the origins of fast radio bursts is ongoing, with astronomers using powerful telescopes and innovative techniques to uncover their secrets. Each new detection brings us closer to understanding these enigmatic signals and their role in the universe. As we continue to explore, one thing is clear: fast radio bursts are yet another reminder of how much we still have to learn about the cosmos. Next, we'll explore another high-energy phenomenon, cosmic rays, and their connection to the universe's most powerful events. Stay tuned. Now, shifting our focus to another fascinating aspect of the universe's high-energy phenomena, let's explore the role of cosmic rays. These high-energy particles, traveling through space at nearly the speed of light, are thought to originate from some of the most powerful events in the cosmos, such as supernovas and gamma-ray bursts. When a massive star explodes in a supernova, it doesn't just release light and heat, it also accelerates particles to incredible speeds, sending them hurtling across the universe as cosmic rays. These particles carry immense energy, often millions of times greater than anything we can produce in particle accelerators on Earth. Cosmic rays are not just a curiosity of space, they have a direct impact on our planet. When these particles collide with Earth's atmosphere, they create showers of secondary particles, some of which reach the ground. This process plays a role in everything from cloud formation to the production of rare isotopes in the atmosphere. In fact, cosmic rays are one of the reasons we detect traces of carbon-14 in organic materials, which scientists use for radiocarbon dating, but their influence doesn't stop there. Cosmic rays can also affect satellite electronics and even pose a radiation risk to astronauts in space, making them a key consideration for space exploration. Beyond Earth, cosmic rays are thought to play a crucial role in shaping the universe. They contribute to the heating of interstellar gas, which can influence star formation and the evolution of galaxies. Some scientists even speculate that cosmic rays could be responsible for triggering chemical reactions in space, potentially leading to the formation of complex molecules necessary for life. This makes them not just a byproduct of cosmic explosions, but an active participant in the universe's ongoing story. As we continue to study cosmic rays, we uncover more about their origins and their impact on both the cosmos and our daily lives. From their connection to supernovas and gamma-ray bursts to their influence on Earth's atmosphere and beyond, these high-energy particles remind us of the intricate web of interactions that define our universe. Next, we'll turn our attention to the search for extraterrestrial life and how studying energetic events like gamma-ray bursts might hold the key to answering one of humanity's biggest questions. Stay with us. Now, let's take a fascinating leap into the realm of possibility. Could gamma-ray bursts and other high-energy cosmic events hold clues to the existence of extraterrestrial life? It's a question that has intrigued scientists and dreamers alike. While gamma-ray bursts are typically associated with the violent deaths of massive stars or the collisions of neutron stars, some researchers have proposed that these bursts could also serve as cosmic beacons, signaling the presence of advanced civilizations. Imagine a civilization so advanced that it could harness the energy of a gamma-ray burst, using it as a form of interstellar communication or even as a power source. While this idea might sound like science fiction, it's rooted in the idea that highly energetic events could be manipulated or detected in ways we're only beginning to understand. One intriguing theory suggests that advanced civilizations might use gamma-ray bursts as a way to announce their presence across vast distances. Given the immense energy and brightness of these events, they could be seen from billions of light years away, making them ideal for sending signals across the cosmos. If a civilization could control or predict such bursts, they might use them as a kind of cosmic flare, visible to anyone with the technology to observe them. This raises the tantalizing possibility that some gamma-ray bursts we detect might not be natural at all, but rather the work of intelligent beings far beyond our understanding. But the connection between gamma-ray bursts and extraterrestrial life doesn't stop there. These energetic events could also play a role in shaping the conditions necessary for life to emerge. For instance, the heavy elements produced during neutron star collisions, events that often trigger gamma-ray bursts, are essential building blocks for planets and life as we know it. Without these elements, the universe would lack the diversity of materials needed to form complex structures, including living organisms. In this way, gamma-ray bursts might not just be destructive forces but also cosmic catalysts, setting the stage for life to flourish in distant corners of the universe. Of course, the search for extraterrestrial life is still in its early stages, and gamma-ray bursts are just one piece of the puzzle. But by studying these events, we're not only learning about the universe's most powerful explosions, we're also opening the door to new possibilities. Could gamma-ray bursts be the key to finding life beyond Earth? It's a question that keeps scientists looking to the stars, searching for answers in the light of these incredible cosmic phenomena. Next, we'll wrap up our journey with a look at the sheer beauty of these energetic events and what they reveal about the universe's most awe-inspiring moments. Stay tuned as we bring our exploration of the universe's most energetic events to a close. Let's take a moment to appreciate the sheer beauty of these cosmic explosions. While we've spent much of our time discussing the science and mystery behind phenomena like gamma-ray bursts, supernovas, and neutron star mergers, it's impossible to overlook the breathtaking spectacle they create. These events are not just powerful, they're also some of the most visually stunning displays in the cosmos. Picture a supernova, the explosive death of a massive star, lighting up an entire galaxy with its brilliance. For a brief moment, it outshines billions of stars combined, painting the darkness of space with vibrant colors and swirling clouds of gas and dust. Or imagine a gamma-ray burst, a flash of energy so intense that it can be seen from the edge of the observable universe, cutting through the void like a cosmic lighthouse. And then there are neutron star collisions, where two incredibly dense objects spiral together in a dance of destruction, sending ripples through space-time and scattering heavy elements like gold and platinum across the cosmos. These events remind us that the universe is not just a place of chaos and destruction, it's also a canvas of incredible artistry. The forces at play in these explosions create patterns and structures that are as beautiful as they are powerful. From the intricate shock waves rippling through space to the glowing remnants left behind, each explosion tells a story of creation and transformation. But beyond their visual splendor, these events also reveal something profound about the universe itself. They show us how interconnected everything is, from the birth and death of stars to the formation of planets and the elements that make life possible. In a way, these cosmic explosions are not just endings, they're also beginnings, seeding the universe with the building blocks for new stars, new worlds, and perhaps even new life. So, as we reflect on these 25 facts about the universe's most energetic events, let's not forget to marvel at the beauty they bring to the cosmos. These explosions are a reminder of the universe's boundless creativity and power, and they inspire us to keep looking up, searching for answers, and appreciating the wonders that lie beyond our world. Thanks for joining us on this journey through the universe's most awe-inspiring moments. Don't forget to like, subscribe, and hit the notification bell for more cosmic adventures. As we wrap up our journey through the universe's most energetic events, it's clear that these phenomena are not just awe-inspiring, they're fundamental to understanding the cosmos. From the mind-boggling power of gamma-ray bursts to the dazzling beauty of supernovas and the cosmic gold mines created by neutron star collisions, each event reveals a piece of the universe's grand puzzle. These 25 facts have shown us how these explosions shape galaxies, forge the elements that make up our world, and even influence the very fabric of space-time. They remind us that the universe is a place of both destruction and creation, where chaos gives birth to beauty and mystery fuels discovery. But the story doesn't end here. Every explosion, every burst of energy, and every ripple in space-time leaves behind clues for us to uncover. What else might these cosmic events teach us about the origins of the universe? Could they hold the key to understanding dark energy, the expansion of the cosmos, or even the possibility of life beyond Earth? The more we learn, the more questions arise, and that's what makes space exploration so thrilling. So, what's your take on these cosmic wonders? Which of these events left you the most amazed, or maybe even a little terrified? Let us know in the comments below, and don't forget to share your thoughts with fellow space enthusiasts. If you're hungry for more cosmic mysteries, hit that subscribe button and ring the notification bell so you never miss an adventure into the unknown. The universe is full of secrets waiting to be uncovered, and we're just getting started. Thanks for watching, and keep looking up because the stars have so much more to show us. Now, let's take a closer look at the science that makes these cosmic spectacles possible. Behind every gamma-ray burst, supernova, and neutron star collision lies a fascinating web of physics that shapes the universe as we know it. One of the most striking features of gamma-ray bursts is the presence of relativistic jets. These are narrow beams of particles and radiation that shoot out at nearly the speed of light, powered by the immense energy released during the collapse of a massive star or the collision of neutron stars. These jets are so powerful that they can outshine entire galaxies for a brief moment, and their formation is tied to the extreme conditions found in these cosmic events. Another key player in these energetic phenomena is the shock wave. When a massive star explodes as a supernova or when neutron stars collide, the explosion sends out shock waves that ripple through space. These shock waves can heat surrounding gas to incredible temperatures, triggering nuclear fusion and creating heavy elements like gold and platinum. In fact, much of the gold in your jewelry likely came from a neutron star collision billions of years ago. It's a reminder that the universe isn't just a place of destruction, it's also a cosmic forge, creating the building blocks of planets, stars, and even life itself. Nuclear fusion, the process that powers stars, also plays a crucial role in these events. During a supernova, the intense heat and pressure cause lighter elements to fuse into heavier ones, releasing vast amounts of energy in the process. This energy fuels the explosion and drives the shock waves that spread through space. In neutron star collisions, the extreme conditions can even produce exotic forms of matter, like quark-gluon plasma, giving scientists a glimpse into the fundamental forces that govern the universe. Understanding these processes isn't just about satisfying curiosity, it's about piecing together the story of how the universe works. From the birth of elements to the behavior of matter under extreme conditions, these events are like cosmic laboratories, revealing secrets that we can't replicate on Earth. And as we continue to study them, we're not just learning about the universe, we're learning about ourselves and our place in the grand tapestry of existence. Now, let's shift our focus to the incredible tools and technologies that allow us to study these mind-blowing cosmic events. Without the right instruments, much of what we know about gamma-ray bursts, supernovas, and neutron star collisions would remain a mystery. So, what exactly are scientists using to unlock the secrets of the universe's most energetic phenomena? One of the most important tools in this cosmic detective work is the Space Telescope. Satellites like NASA's Swift and Fermi are specifically designed to detect gamma-ray bursts. Swift, for example, can quickly pinpoint the location of a burst and observe its afterglow across multiple wavelengths, from X-rays to visible light. Fermi, on the other hand, specializes in capturing the highest energy gamma rays, giving us a clearer picture of these explosive events. These telescopes act as our eyes in the sky, allowing us to witness cosmic fireworks that would otherwise go unnoticed. But it's not just about telescopes. Gravitational wave detectors like LIGO and Virgo have revolutionized our understanding of the universe. These incredibly sensitive instruments can detect ripples in space-time caused by cataclysmic events, such as neutron star collisions. In fact, the first detection of gravitational waves from a neutron star merger in 2017 was a game-changer. It not only confirmed the origin of short gamma-ray bursts, but also provided a new way to study the universe, one that doesn't rely on light. On the ground, observatories like the Very Large Telescope in Chile and the Keck Observatory in Hawaii play a crucial role. These powerful telescopes can observe the afterglow of gamma-ray bursts and study the chemical signatures left behind by supernovas. By analyzing the light from these events, scientists can determine the composition of the material ejected into space, shedding light on how elements are formed in the universe. Recent advancements in technology have also opened up new possibilities. For instance, the upcoming James Webb Space Telescope promises to peer deeper into the cosmos than ever before, potentially revealing the earliest gamma-ray bursts in the universe. Meanwhile, next-generation gravitational wave detectors like the planned Einstein telescope aim to increase sensitivity, allowing us to detect even fainter signals from distant cosmic events. These tools aren't just gadgets, they're extensions of human curiosity. They allow us to explore the universe in ways that were once unimaginable, bringing us closer to answering some of the biggest questions in science. From the birth of black holes to the creation of heavy elements, every discovery made with these instruments adds another piece to the cosmic puzzle. And as technology continues to evolve, who knows what other secrets of the universe will uncover next? Now, let's take a moment to look ahead and imagine what the future holds for space exploration, especially when it comes to studying the universe's most energetic events. These cosmic phenomena aren't just fascinating, they're also key to unlocking some of the biggest mysteries of the cosmos. As technology continues to advance, the way we explore and understand these events is set to change dramatically. One of the most exciting prospects is the development of even more powerful telescopes and detectors. For example, the James Webb Space Telescope, which recently began its mission, is already providing unprecedented views of the universe. But this is just the beginning. Future missions like the European Space Agency's Athena X-ray Observatory will allow us to study gamma-ray bursts and other high-energy events in even greater detail. These tools will help us peer deeper into space and further back in time, potentially revealing the very first gamma-ray bursts that occurred after the Big Bang. Another area of focus is the improvement of gravitational wave detectors. Current instruments like LIGO and Virgo have already transformed our understanding of neutron star collisions and black hole mergers. However, next-generation detectors such as the Einstein telescope and the Laser Interferometer Space Antenna, or LISA, promise to be even more sensitive. These advancements could allow us to detect gravitational waves from events that are currently beyond our reach, opening up entirely new avenues of research. But it's not just about building better tools, it's also about collaboration. Space exploration is increasingly becoming a global effort. International partnerships, like those between NASA, the European Space Agency, and other space agencies around the world, are essential for tackling the challenges of studying these energetic events. By pooling resources and expertise, scientists can achieve far more than they could alone. This spirit of cooperation is crucial for missions like the Square Kilometre Array, a massive radio telescope project involving multiple countries, which will help us study the aftermath of gamma-ray bursts and other cosmic explosions in incredible detail. Studying these events also has practical implications for the future of space travel. For instance, understanding the effects of gamma-ray bursts and other high-energy phenomena could help us develop better shielding for spacecraft, protecting astronauts from harmful radiation. Additionally, the heavy elements produced by neutron star collisions like gold and platinum could one day be mined from asteroids, providing valuable resources for future space missions. As we continue to explore the universe's most energetic events, we're not just satisfying our curiosity, we're also paving the way for the next era of space exploration. From uncovering the origins of the cosmos to ensuring the safety of future space travelers, the discoveries we make today will shape the way we explore the universe tomorrow. And with each new breakthrough, we're reminded that the universe is full of surprises just waiting to be discovered.